So we'll summarize all the Fourier series properties and lectures that we have seen so far. But the complex exponential, which are the phasors, were special mainly because of the two properties that they satisfied, which is the orthogonality and the boundedness. So not only two phases of different frequency are orthogonal, but you take any phasor, and if the scaling factor of phasor is 1, then it is always bounded. What is the magnitude? The magnitude is always 1. So you don't get an exponential which grows unboundedly or which decays continuously. So we have a nice bounded signal. So this helped us in deconstructing any given signal in terms of these orthogonal signals. We started treating them as bases, and then we decomposed any signal in terms of these phasors. So the first decomposition that we performed was for periodic signals, okay? And the decomposition that we got is what we call as the Fourier series. So given any signal z of t, we said that we'll decompose that in terms of the phasors which are harmonics of a fundamental frequency. This is the fundamental frequency, okay? And given a fundamental frequency, we'll pick its harmonics, which is 0 omega, plus or minus omega, plus or minus 2 omega, and so on. And then just simply multiply those with the corresponding magnitude, and this coefficient can be a complex number, it can be a real number, and so on. So we'll decompose this z of t, any z of t which is periodic, in terms of harmonics and scale each of the harmonics with a particular coefficient. And this is how we said we can represent any periodic signal in terms of the Fourier series. And how to find the coefficients? The coefficients are nothing but simply scaled inner products. And how do you find the inner product? You just take the projection of the signal z of t onto a particular phasor. That's all. So this is what we refer to as the Fourier series representation. You take the fundamental frequency and its harmonics and then represent the signal in terms of that, and then you find the coefficients just by projecting that particular signal onto the phasor. And the AK that we get denotes the component of the phasor which has a frequency k omega. Now, one thing that we saw was that it may be required in certain cases to have infinite number of phases. That is, this k may have to go from minus infinity to infinity in order to fully represent this signal z of t. And if you don't use the infinite number of phases to actually compute z of t, it may happen that you will find out ripples in the representation, and that is what we called as the Gibbs phenomena. So if you have only finite number of them, especially in simulations, and when you see in practice, you may not be able to add infinite number of them. You may be adding only a finite number of them, because of which you might end up getting what is called as the Gibbs phenomena instead of observing the actual signal itself. From this, we also were able to define what is known as the bandwidth of a signal and what is meant by spectrum. If you just simply plot all these Fourier series coefficients, the AKs, they represent the spectrum of the signal, okay? And if you say that the spectrum is finite length, meaning it is non-zero only for a finite values of k and 0 everywhere else, then you can find a bandwidth which is finite, which is not infinity, right? And that's how we define spectrum and bandwidth. And going forward, we also said that the representation of the signal in Fourier series is exactly the same signal. So this is z of t, and whatever we have on the right hand side is still z of t, right? Both are equal. So if I compute the power here, it has to be equal to the power that I compute here, and that is all what is Parseval's theorem. So you compute the power in time domain, it has to be equal to the power on this side, which is nothing but the power of several orthogonal signals. So you can just add up the power of the individual orthogonal signals. So we have the Parseval's theorem, which simply says you just add up the power and you are done. So power or energy representation in any of the domain is exactly the same. That is what Parseval's theorem is. And all these analysis will work only if the Fourier series converges and it exists. And we saw a set of conditions for which this is true, and we call that as Dirichlet conditions. So the Dirichlet condition ensured that the inner product exists, and whenever there is a discontinuity, we saw that the Fourier series will converge to the average of the left and right limits. So this is what Dirichlet conditions told us, that you should have a signal which is absolutely integrable in one period, and it should have finite number of discontinuities and finite number of minima or maxima within one period. So that is Dirichlet condition. As long as these are satisfied, these are all sufficient conditions. As long as these are satisfied, you can always ensure that the Fourier series of the particular signal will exist and that will converge at every point. Now from this, we also defined what is known as the frequency response of an LTI system. Remember, all of this we started analyzing only to find out what is the output of an LTI system, how to characterize that. And going back to that, we said that the output of an LTI system for an input which has some Fourier series coefficient is simply nothing but the product of the Fourier series coefficient with the corresponding eigenvalue of the LTI system. That is, if I have an input e power j k omega t to the LTI system, the output of the LTI system will simply be the eigenvalue multiplied with this input, because this is an eigenfunction, right? So this is the output of the LTI system, and this is what we refer to as the frequency response of the LTI system. How does the LTI system respond to different phasors of different frequencies? So that response is quantified by this eigenvalue, and that is what we refer to as the frequency response. And the frequency response is simply nothing but integral h of t e power minus j k omega t dt. So this is the frequency response. So once you know the frequency response, you can always find the output of the LTI system for any given periodic input just by using the Fourier series coefficient. And we also saw some properties of the Fourier series coefficient. The important property is that if you just multiply them in the time domain, then in the Fourier series domain, it simply is the discrete convolution of the Fourier series. And for even signals, you can expand the signal only in terms of cosines. Remember, cosines are also orthogonal, okay, and they are also bounded, which means we can also use them as bases, but that makes sense only when you can represent the signal which is even, because cosines are all even signals. So when you add up even signals, you will get only even signal. So as long as your signals are even, you can represent that using completely cosines. And of course, these Vk values can be complex. It's not necessarily real always. Similarly, for odd, you can represent that using sines, because sine is also again a set of orthogonal signals, once again bounded. There is no B0 term, if you notice here, because when omega is equal to 0, sine 0 is 0, and of course the DC value is even, right? The DC value, which is a constant value, is not an odd signal. So it cannot be part of any odd signal. So if somebody says that they have an odd signal, you can be clear always that the DC component that is present in the odd signal is always 0. The DC component, the even signal, can be non-zero, but for an odd signal, the DC component is always 0. So this is one thing that you can always use to check if your analysis is right or wrong. And this is the summary of the properties of the Fourier series coefficients and the corresponding operation that we do in the time domain, right? So whatever symmetry that we have in the time domain, there is a corresponding symmetry in the Fourier series coefficients. And more importantly, if we have a real signal, then the Fourier series coefficient is conjugate symmetric. If you have an imaginary signal, then the Fourier series coefficient of conjugate asymmetric. This is very, very important, because in practice, most of our signals are real, which means most of the Fourier series coefficients that we would compute end up being conjugate symmetric. So we have to keep that in mind. And if you modify something in time, of course, the Fourier series coefficients will change accordingly. For example, time shift becomes only a phase shift. The frequency components do not change, right? Because you are just moving in time, periodicity does not change, so frequency also does not change. Whereas scaling in time changes the frequency components that are present. Then we saw what happens to the bandwidth and so on. So this concludes Fourier series. Now, remember, we started Fourier series by choosing a particular set of these eigenfunctions. Among all possible eigenfunctions, that is e power j omega t, where this omega can go from minus infinity to infinity in a continuous fashion, that is, this omega belongs to R, any real number, but we picked only integers. That is, we said that we will choose omega to be equal to some k times some omega naught, where k is the set of all integers, right? So we picked only a subset of all possible frequencies. Now what if we pick the entire set? What if we let omega be from minus infinity to plus infinity? So if this is our choice, then how do we define the inner product? So these are the questions that we'll answer next. So this will be our next choice of basis functions, and once we find out how to tackle the inner product problem here, we'll know how to find out another set of decomposition for any given signal, and that is what we'll call as Fourier transform.